Now, what we're looking at is, what we're working towards is the trapezoidal method. Why trapezoidal method? Well, surprise, surprise, because we're going to be working with trapezoids. How so? So remember, what we're doing is that we're trying now to use a top for each of those slices that is not a horizontal top, but it's a slanted line. So let's look at our function. So we're trying to compute some integral related to this function. We're going to consider typical strip, and what we're going to do is we're going to join the two values corresponding to the two endpoints of the strip, xn minus 1 and xn. Now here n doesn't mean the last point, it just means any one of the strips that we're using. Of course, no matter what strip we use, the width of that interval is still going to be delta x. Now what we're going to do is we're going to look at the value of the function at xn minus 1, so it'll be f of xn minus 1, whatever that is, and the value of the function at xn will be some f of xn, and we're going to approximate the area under the curve between those within that slice by joining the endpoints. So we're going to use this particular shape. So now there is where the trapezoid is coming in. So we don't have rectangles anymore, we have trapezoids. But the area of a trapezoid is something fairly easy, whose formula we know, or should know, and therefore we can work with it, right? So, well, what is the area of a trapezoid? Well, the area of a trapezoid is given by the sum of the two bases, in this case the left and the right edges of our trapezoid, of our quadrilateral, so two vertical lines, divided by 2 and multiplied by the height of the trapezoid, which in this case is actually going to be the delta x. If you're not convinced, you may want to pause once again and look at the area of the trapezoid and recognize and realize and be convinced that that is the formula for it. So what we can do is we can apply that formula for each one of the slices, right? All we have to do is figure out what is the value of the function at each of those points that generate the slices. Notice that by doing this, we're losing the balancing act of the midpoint, right? The midpoint was right in the middle, so hopefully some part of the function was above it, some part of the function was below it, and it provided some kind of equilibrium. But in this case, as you can see right here in front of you, the trapezoid may end up being totally above the function in the whole strip. So all we can do is we can hope that as we go from strip to strip, those things will be equalized. But that means that we have to hope that our function has quite frequent changes of concavity, which is not always the case, right? So probably, although this method looks like it's an improvement, it may not be one. But anyway, let's see what this leads to. So now that we have the area of one of the slices, or we have approximated the area of one of the slices, what we need to do is add up all the slices. Of course, we're not going to take the limit. We're just going to take the sum of all those slices. So the picture we have in front of us is this one. The area we're trying to compute is the area under the red curve between, in this case, will be 1.5 and 7.5. But we're going to do that by using the areas of all those trapezoids. Notice that this time we're going from the left endpoint, which is our good old A at 1.5 in this case, to the right endpoint, which is at 7.5. And we're using as points at which to evaluate the function the transition points from one slice to the next. Okay, so in computing our integral from a to b of f of x, we're going to say, all right, that's going to be approximately equal to the sum of all those areas, and we're going to use all these values x0, x1, x2, etc. Notice I'm starting at x0 because really x0 is the left point and it just denotes the beginning, and then x1 denotes the end of the first trapezoid, x2 denotes the end of the second trapezoid, and so on and so on. So if we use all those numbers and we apply the formula for the area of trapezoid to each one of those, you'll notice that x0, the first one, and xn are being used only once, namely for the first and the last trapezoid. But all the ones in between are being used twice, right? Because they belong both to the slice which is on their left and the slice which is on their right. So if you work out the algebra of adding all the areas of these trapezoids, you end up with this formula. Now let's look at this formula for a second. First of all, notice that what we have here in the denominator, we have a 2 coming, of course, from the 2 in the denominator of the area of a trapezoid. But you can think of it by noticing that for each trapezoid, we need 2 of those xi points. Okay, so keep that in mind because that's going to come in handy for the next method. And then what do we have? Well, we have the leftmost point x0, which is our old a, gets evaluated only once at f of x0. The last point, which is xn, which is our good old b, is also evaluated only once at as f of xn, and then all the values in between get evaluated twice. So it's a long, probably tedious formula, but it's one that has a certain pattern to it and one that can be fairly easily implemented. In fact, it's one for which I'm sure you'll be able to write yourself a very short program to implement it. And here is the trapezoidal method. There is a formula, not too complicated, but remember we have that problem with the trapezoids not actually providing a balancing act. So probably this is not going to be a great method. The idea is good though. Let's see if we can push it further.